Good afternoon, everybody. So welcome back to the afternoon session of day 2 of the HydroGNSS workshop. So this afternoon for this session 3, we're going to hear all about mission synergy from other GNSS-R missions. The chairs for today's session, for this session, are Maria Paola Clarizia from ESA, and Davide Comite from Sapienza University of Rome. So I'll hand over to the chairs.
Thank you very much, Peter. Hello, everybody. I'm Maria Paola Clarizia from ESA. Thanks for sticking around for this session, which is about the mission synergy. Our first speaker is Professor Adriano from the Polytechnic University of Catalonia, and he's going to talk about GNSS-R experience from FSS-CAT and MIR L1 plus L5. So the Adriano's presentation is going to be a recorded one. And I don't know if he's present or not.
He should be on the phone. He was telling me that he's on the phone, but we cannot hear him.
Polytechnic Catalonia in Barcelona, Spain. Hello. My name is Adriano and I'm with the Universitat Politècnica de Catalunya in Barcelona, Spain. I'm going to talk about the GNSS-R soil moisture retrievals from FSS-CAT, MIR, and others, and the lessons that we have learned over the past 14 years. The outline of this presentation is the following. First, I will make a brief introduction on where we were coming from, and then I will describe some results on the GNSS-R sensitivity to soil moisture, to surface roughness, to vegetation, and then I will explain the lessons that we have learned from the MIR instrument and from FSS-CAT. And then I will conclude with a summary of the lessons learned. So we start working in passive microwave remote sensing back to the early 90s in something that later became the ESMOS mission, which stands for Soil Moisture and Ocean Salinity. We work from the instrument concept, including calibration, image reconstruction, etc., to the retrieval of geophysical parameters and the development of novel applications. In particular, and because it's relevant for this presentation, we develop algorithms to downscale the ESMOS soil moisture maps down to a much smaller scale. In this case, you have an example of the region of Catalonia and the Ebro River basin down to 250 meters. It's worth mentioning that all these activities are done in conjunction with the Barcelona Expert Center. In the field of GNSS-R, we start working back to the year 2000. Also, we have a strong background in instrument design and developing applications. And in particular, in the field of soil moisture, we start working in the year 2008. So our first experiment related to soil moisture dates back to the year 2008, when we were conducting the Grajo experiment in Salamanca, in the Remedus, in a site that is used for Calval of SMOS. And at that time, in addition to the LoRa radiometer, we put 2 GNSS-R instruments, Gripau and Smigol. And one of the first results that surprised us was the sensitivity that the peak of the delayed Doppler map exhibit to changes in the soil moisture, as high as 42 dB per 100% change in the soil moisture. Later, we processed TDS1 data, and at a global scale, we got more or less similar results on the order of 38 dB per 100%. We kept analyzing TDS1 data and found some anomalies, notably in very, very dry areas in the Saharan desert. For example, these 2 tracks here in the Libyan desert, with exactly the same conditions in terms of soil moisture, no vegetation, surface roughness, no topography effects, etc., show very, very distinct reflectivity values by about 8 dB one from the other. And both measurements were acquired nearly simultaneously. So here, there must be something else. Maybe because the terrain is so dry, the waves penetrate more, and we have volume scattering. There are inhomogeneities in the soil dielectric profile, and then maybe the reflection is actually taking place in an underground moisty layer rather than in the surface. So in the project GNSS-R for land, in which we participated, we developed a GNSS-R simulator for land, and one of the things that we quantify was the sensitivity or the change in the DDM peak with respect to the soil moisture. And then it became very clear why we were obtaining different results. If the measurements were acquired in drier areas, then we get much higher sensitivities, up to 43 dBs or more per 100%. However, if we go to moisture regions, the sensitivity dropped to 8 to 9 dB per 100% soil moisture change. And on average, it was about 17 dB. So the first lesson that we learned is that any soil moisture retrieval cannot perform using linearized models. Their range of validity is very limited. When trying to analyze the sensitivity to surface roughness, this is what we got with the simulator, and we saw even larger sensitivity to surface roughness, even when no topography effects were taken into account. So we see that for an RMS going from 0.5 to 4 centimeters, then the drop is almost 20 dB. Then we conducted some experimental results in Lleida, or to the west of Barcelona, with an GNSS instrument working at L1 with 1 millisecond coherent integration time and 1 second incoherent integration time. We also conducted in situ measurements for the surface roughness for the vegetation, and the lessons that we learned were that in situ measurements for the surface roughness were not suitable at all, no matter if the surface roughness was characterized with mechanical profilers, with laser profilers, no matter how many measurements we conducted per plot, etc. We also arrived to the conclusion that maybe the reflection was taking place in an underground layer, so it looked like flatter than the actual air to soil interface, that these volume scattering effects probably could not be neglected. We also attempt to do a correction as it is done for SMAP, like with a constant H factor to account for the roughness, and we found that it was not suitable at all. We found, however, the possibility to perform some ad hoc corrections for the surface roughness, but it was dependent from one plot to the other, so it was very difficult to generalize. So at that point, it looked like the surface roughness corrections were a showstopper for the accurate retrieval of soil moisture. We also analyzed the sensitivity to vegetation effects, and by processing TDS1 data at global scale, we found that the larger the vegetation, as parameterized with the NDVI, the lower the reflectivity or the SNR. Actually, it dropped by about 4 dB when the NDVI changed from 0 to 1. We thought that this was a little bit too low, probably because when doing all these observations, there were many areas in the world where the vegetation exhibited a high NDVI, but the vegetation was not really opaque in terms of the electromagnetic wave. So we conducted another experiment in La Fageda d'en Jordà in Catalonia. It is a beech forest. The experiment took place during more than a year, from the fall of 2015 to 2016. And what you have here is the change in the CN0 as a function of the NDVI and as a function of the elevation angle. So, of course, the lower the elevation angle, the less signal we get because of the attenuation, but also the larger the NDVI, the less power that we get. And on average, the slope was about 17 to 21 dB for a change in the NDVI of unit. We also, in the project GNSS for land, conducted some sensitivity analysis. To do that, we included the model provided by the Tor Vergata University and included the attenuation as a function of the VOD, and found again that it was a very nonlinear function and it depends on the range of VODs that we were encountering. Also, trying to correct for vegetation effects using simplified models like the Tau Omega model that is used with success in L1 microwave radiometry, we think it's not appropriate, at least for dense vegetation, as it tends to overcorrect vegetation effects. So in general, we need techniques to better predict vegetation corrections. In preparation for the CubeCat2 CubeSat mission, we put an engineering model of the Picaro payload on board an stratospheric balloon experiment. This instrument was capable to collect L1 and L2 GPS GLONASS and Galileo, and both left and right circular polarized signals. So one of the things that we encounter is that the signal that we were receiving was nearly independent from 0 to 20 kilometers height. This suggested that a non-negligible coherent component was present. The other thing that surprised us is that when looking to the time series, the value of the reflected power jumped randomly among 4 different values that we attributed to different scattering mechanisms, the strongest ones, of course, being the reflection on the soil surface. But we also hypothesized that other scattering mechanisms occur in the canopy and soil and in the soil trunk. Since we were able to track the phase, we found that for low elevation angles from 30 up to 43 degrees, actually the phase was corrected, but the intensity was clustered into different values in accordance to the behavior that we encounter here. When the elevation angle increased, so the reflection was closer to the perpendicular direction, then the reflection became more incoherent, and then the clusters of points are not as evident. So we found that the coherent scattering varied depending on the incidence angle, depending on signal, etc., but values of up to 38% were not strange. We also checked and saw that the reflectivity values varied depending on the signal that we were tracking. On the left-hand side, we have different GPS signals, all emitted by the same satellite, so the nominal specular reflection point is exactly the same, but this is for L1CA, L2C, L1PY, and L2P. So, as you can see, the values of the reflectivities are different depending on the signal that we are using. And for example, these two that correspond to the PY signal are very different from these two here, despite C and D correspond to L1 and L2. And these ones are at different frequencies and more or less the same value. In this case, we have other examples for GLONASS, and this one here is for Galileo, but obviously it's impossible to compare or to directly compare because the specular reflection point is in a different location. We also conducted some polarimetric measurements and computed the ratio of the copolar to the cross-polar pattern, or the copolar to the cross-polar receive power, and found different values of the polarimetric ratio. So values from 4 to 14 were found for high elevation angles, and it depends basically, this is for the forest, for the lakes, much higher values were encountered. We also conducted some simulation results and found that for low elevation angles, the dominant effect is the soil scattering, and as the elevation angle increases, this coherent component increases, but starts becoming more comparable with that, to the reflection coming from the leaves and the branches and so on. Also, the reflection from the soil is more important when the density of trees per hectare in this simulation decreases, because the opacity of the vegetation is less important. And now, let's talk about the lessons that we learned from the MIR instrument. The MIR instrument, it includes two 19-element arrays with 4 beamformers per array, 2 at L1E1 and 2 at L5E5A. I have to say that the instrument basically automatically steers the beam towards the direct satellite and the specular reflection. The calibration is performed internally by injecting PRN signals. The experiments were conducted in New South Wales, in Australia, in the Janko area that it's also used for ESMOS Calval activities, and in two areas named Janko A and Janko B. We conducted 2 flights over these regions, one in very dry conditions without any rain for more than 3 months, and the other in very wet conditions to the point that there were water ponds on the surface in some areas. And these are some of the results that we saw in one of the tracks for the reflectivity, for the moving standard deviation of the reflectivity, and then the moving standard deviation minus the reflectivity, which is a measure of the noise to signal ratio. So let's recall that the correction for the surface roughness could not be estimated from physical measurements, as we were at that time more convinced that L-band waves penetrate in the soil. So our approach was to use very short integration times so that the properties of the terrain in terms of roughness, vegetation, etc., can be assumed to be constant. So even with high receive powers, the SNR is limited by the speckle noise because we have this coherent component, as we saw in the stratospheric balloon experiment. So we use the moving standard deviation to estimate the noise to signal ratio, which is the inverse of the signal to noise ratio, and we compute the increase in the noise to signal ratio with respect to the one that will be obtained only by speckle noise as a proxy of the surface roughness. So on the left-hand side here you have the histogram of roughness, estimated roughness at L1 in blue color, at L5 in brown color. And here is this is for 20 milliseconds incoherent integration time. This one is for up to 1 or 5 seconds incoherent integration time. So what is occurring here is that the SNR, in principle, it's improving because we are performing a lot more averaging, but then the statistics depart significantly. So long incoherent integration times alter the statistics, so we restrict ourselves to short integration times on the order of 20 milliseconds, from which we estimated the effective surface roughness to be included in the retrieval algorithm. And these are the results. We use the NDVI as the best proxy that we can use to account for vegetation effects. We also have the soil moisture downscale from SMOS, in this case down to 20 meters. And here are the different retrievals at L1 and L5 and the standard deviation of the retrieved soil moisture with respect to the downscale soil moisture. For different cases, case 4 in blue is only taking into account the reflectivity and the incidence angle. Case 3 includes the NDVI as well. Case 2 includes the moving standard deviation as a proxy for the surface roughness. And the case 1, which is the one that performs the best, includes the reflectivity, the moving standard deviation as a proxy of the roughness, the incidence angle, and the NDVI. It's also worth noting that L5 is obtaining better results than L1, probably because the effects of surface roughness are less important. And this is despite the directivity of the antenna is a little bit smaller at L5 than it is at L1. I have to say that at L1 is above 20 dBs, at L5 is about 18.5 dB. Another of the lessons learned from Mimir is that we can also retrieve the vegetation height because the waveform spreads, and in some cases, depending on the incidence angle and the height of the vegetation, when it is very high, you can even see 2 peaks in the receive waveform. These 2 peaks coming from reflections probably on the top and on the bottom of the vegetation. And here you see the profile of the retrieve vegetation height using an artificial neural network. In black, the GLAD ground truth, this is a LiDAR, and the error, which has an RMS on the order of 4.07, 4.25 meters. The lessons learned from FSSCAT. FSSCAT is a 2 6-unit CubeSat mission that was the winner of the Copernicus Masters competition in 2017 and the ESA Sentinel Small Satellite Challenge. The first of the CubeSats, CubeCat 5A, includes a GNSS-R and microwave radiometer at L1, and the second includes an hyperspectral imager, HyperScout 2, which includes bands in the visible near infrared, thermal infrared, and it was enhanced with the VSAT-1 experiment for cloud detection. The goals are soil moisture, ice extent, concentration, thickness, and to test novel techniques for future satellite federations. And all the data is freely available. You can check these links here. So the lessons learned from FSSCAT. In a nutshell, we tried 4 different approaches using artificial neural networks. The first one, just using multispectral imagery, the so-called triangle method. And we were able to find some retrieval errors on the order of 0.4%. If we use microwave radiometry and multispectral imagery, the error improved a bit to 7.4%. We also tried to use GNSS-R only, and the error was larger than in the previous case, 1.7%, and of course only on the strips, on the tracks of the specular reflection point. And the last of the approach include the combination of the microwave radiometer plus the GNSS-R data and multispectral imagery. Multispectral imagery was used to derive the NDVI. We use MODIS because the images from HyperScout 2 were not available, and they were not available over all the regions in which we were able to collect data from FMPL2. And we use also ECMWF skin temperature to correct for the antenna temperature from the microwave radiometer. And these are the results. In this case, we obtain a 6.3% error. The expected, when translating these results from MIR and FSSCAT into a satellite mission, these are our best estimates. It's normalized on the x-axis as a function of the number of Fresnel zones that are integrated. So we believe that for an airborne instrument, we can reach a little bit worse than 5% if we integrate up to 25 Fresnel zones. For an instrument on a satellite, we will be on the order of 8.5%. Of course, this is only using a GNSS-R. You can combine that with microwave radiometry data, with veneer and thermal infrared data, and that will lower a bit. In this slide, I'm just summarizing the lessons learned. Thank you for your attention.
Okay, thanks very much, Adriano. It should be online, but I'm not sure.
Again?
Okay, we can hear you, Adriano. Okay, I do not see questions in the chat. So since we are running a bit late, I guess we can go to the next presentation. Thank you, Adriano, for being connected today.
Thank you. Bye.
Thanks again, Adriano. We move on to the next speaker, who's Cong Yin from the Chinese National Space Science Center. And she's gonna talk about soil moisture retrieval from the FY3E GNOS-2.
Thank you.
The floor is yours.
Should I? Can you hear me?
Yes.
Okay. Good afternoon, everyone. My presentation is about soil moisture retrieval from Fengyun 3E GNOS-2. Firstly, I will introduce the background. The Chinese Fengyun 3E is the world's first early morning orbit operational weather satellite. GNOS-2, developed by NSSC on board Fengyun 3E, is the upgraded version of GNOS on Fengyun 3C and Fengyun 3D satellite. The Fengyun 3E was launched in July 2021. Besides the GNSS radio acquisition, the GNOS-2 can additionally provide the GNSS-R measurement. The GNOS-2 could provide both GNSS-RO and GNSS-R products like the fig on the right bottom, the track is the GNSSR and the dots are the GNSSRO. The different color show different systems. And GNOS2 could also provide both spatial and GPS products. And the Galileo will be available in the future, maybe in this year. It has the GPS L1, Beidou B1, and Galileo E1. It could cooperate with the microwave spectrometer on board the same satellite. And it could provide the nearly global coverage with the 8.8 inclination. The primary GNSSR product include the level 1 observation DDM and NBRCS and LES, and level 2 product including the ocean surface wind speed and the mean square slope. The data latency is less than 2 hours. Here is the Fengyun 3E GNOS-R sea surface wind speed product. By compare with the ECMWF and the Haiyang 2 spectrometer satellite, the accuracy is about 1.5 meters per second. And this is the Fengyun 3E GNOS2 GNSSR sea surface wind speed product during the Typhoon Changchu. And in this figure, the comparison with the ECMWF. And the L2 sea surface wind speed data is releasing very soon, maybe by in this March. And then I will introduce the method for soil moisture retrieval. And this is the Fengyun 3E GNOS2 land observation, the DDM. On the left is the observation from Beidou, and on the right is the observation from GPS. It's in the Amazon region. And this is the Fengyun 3E GNOS-R reflectivity. And this picture is the reflectivity, and this region and the Amazon region, we can see the rivers very clearly. And the reflectivity is not only related with the soil moisture, and it also affected by the IGBP land cover and the NDVI. We see this region when the NDVI is very low, so the reflectivity is higher than the other region covered by very heavy biomass. And in these figures, we related the reflectivity to SMAP soil moisture. The observations from South Asia was used to analyze the temporal and spatial variation of soil moisture. These two figures are in August 2021, and the figure in the bottom is in November. For spatial difference, we can see the west of Marwa Plateau is the arid region, and the Ganges River is the humid area. And for temporal variation, we can see in August, it's the flood season. The reflectivity is higher than November, and also the soil moisture by SMAP show the same. This is the GNOS reflectivity with comparison with the GNSS. We can see the GNOS could provide the global coverage, and the variation trend is very similar with GNSS. And the reflectivity was calculated by this formula. We calculated from the L1 data from the DDM calibrated the power and the noise, and the range from receiver to satellite and the transmitter to specular point. And the gain of the reflected antenna. For PTGT, we measured it in the with the station observation in Beijing. This figure is GNOS reflectivity with Cygnus reflectivity, and the upper figure is for Beidou and the lower is for GPS. I should mention that the GNOS reflectivity calculation result is about 5 dB lower than Cygnus reflectivity. So we did the calibration with the lake surface data. Firstly, we selected the lake cover by the ECMWF lake cover lookup table, and then we select the reflections with coherent waveform, like this picture. And the latitude range was 50 degrees to avoid the reflection from ice. The calibration factor could be calculated by this formula. This is the reflectivity on lakes on instance from 0 to 50. And we use this from 0 to 40, the range for calibration factor calculation. And for soil moisture retrieval, we use the neural network training. For input, firstly, we put the calibrated GNOS reflectivity and the MODIS IGBP classification and ECMWF soil type. For vegetation, we use the SMAP vegetation water content and also use SMAP roughness. Then the latitude and the longitude of the specular point and the last month. So we use 8 input and 10 hidden layer. then soil moisture is the only output. And this is the result of 风云3E GNSS-2 soil moisture retrieval, and compare with the SMAP soil moisture for the soil with the vegetation water content less than 5, the IMSE is 0.0586, and for the heavy biomass with the vegetation water content higher than 5, and the IMSE is 0.0908, and the overall IMSE is 0.068. What's next? We will produce the GNSS-R-L2 level soil moisture product, because now we only have the product on sea surface, and we also will do some research on biomass retrieval, and we would also update the topographic map to obtain the data from Tibet Plateau. And last, we will enable the Galileo signal acquisition in 2022. Thank you for your attention.
Thank you. Thank you very much for this nice presentation. I'm giving a look to the chat. I do not see questions, or maybe one, just one now. Okay, Estelle Cardelac is asking, will there be GNSS-2 GNSS-R capabilities in the future FY series?
Yes, we will have 风云 3F, 风云 3G, and also have the GNSS-R on board.
Okay. I have missed this information, but is the mission based on a constellation of satellites?
Pardon?
Is the mission that you are talking about based on a constellation of satellites? There are more than one, or in the future you are thinking to increase the number of satellites to make a constellation?
Yes, yes. And then we will have more observations, because we have 风云 3C, 风云 3D previously, and we will have 风云 3F, 风云 3G, and also a satellite has the lower orbit like Cygnus. It's for the rain observation, but it also has GNSS-2 on board. So we will have more and more GNSS-2 observations. Thank you.
So there is another question by Jens Wickert. He's asking when the next FY satellites will be launched. Do you have
maybe by the end of 2022, this year.
Okay.
If everything is going smoothly.
Okay, there is also another question. It will operate in piggyback mode, probably, right?
Piggyback.
Probably, if you can specify what you mean with the piggyback.
Yes, I don't understand.
An idea, Maria Paola?
Piggyback.
I would think that the question is asking, is it a secondary payload on the spacecraft?
Okay, if it's a secondary one, okay.
Okay, shall we move on in the interest of time?
Okay, thank you.
Okay.
Thank you very much, Cong.
Okay, let's move.
We move on to the next presentation, which is given by Phil Jales from Spire Global. He's going to talk about the Spire activities in GNSSR.
Okay, can I just check my audio is working for you and you can see my slides?
Yes.
Excellent, thank you. So thank you. I'd like to express my gratitude firstly for the HydroGNSS community welcoming us here to talk about the synergies between the HydroGNSS mission and the Spire Global GNSSR missions. So I'm Philip Jales from Spire Global, and I'm going to be talking about our activities in GNSSR. As a brief introduction to who we are at Spire Global, we have a constellation of Earth observation nanosatellites that form a resilient and long-term stable solution to Earth observation. We have satellites in a diverse selection of orbits, and these provide a global coverage with high temporal and spatial sampling. And the constellation provides a good system redundancy by spreading amongst many satellites. We've established this constellation primarily at the moment for GNSS radio occultation, and these observations of the atmospheric soundings feed into operational NWP models on both sides of the Atlantic at the moment. And we're now building up our constellation to additionally measure the Earth's surface through GNSSR. So we are using the Spire's Earth observations, use the GNSS signals as they bend through the atmosphere, and that's the GNSS radio occultation. And this is an input to NWP climate, and also we use ionospheric soundings for space weather monitoring. And we additionally process the reflections from the Earth's surface for GNSSR, and we have a primary focus on soil moisture, sea ice, and ocean roughness. Our real interest is in generating an operational GNSSR constellation utilizing our nanosatellites for dense coverage and to make an impact to NWP, hydrology, oceans, and climate monitoring. So Spire has three types of GNSSR satellites in its constellation, and the first two are what we call conventional GNSSR, and these sense around nadir like Cygnus TDS and HydroGNSS Concept 2. The batch 1 satellites of these, 2 satellites launched at the end of 2019, and then batch 2 satellites were launched about a year later. So these are characterized by having left-hand circularly polarized antennas. And then the second type of satellite that we've got is the grazing angle GNSSR, and this uses Spire's existing GNSS-RO constellation, which then had an on-orbit upgrade to add in the processing for the grazing angle reflections. So in common amongst all three variations is the reception of multi-GNSS systems, not just GPS, to increase the number of observations per receiver. The signal processing is currently tuned for the predominant scattering mechanism. So the conventional GNSSR processes DDM processing and uses an advanced calibration that uses it's a relative calibration system. And the grazing angle GNSSR uses coherent signal processing and outputs a high rate, amplitude, and phase information. So I'm going to firstly pick up on this on the conventional GNSSR satellites, which they sense around nadir and characterized by the left-hand circular polarization. And at the moment, we are doing delayed Doppler map observations on these satellites. So the batch 1 satellites had the goal of trying out the dual deployable GNSSR antennas, and then to increase the amount of antenna gain we could get from our 3U platform to perform antenna beamforming from both the nadir pointing antennas. And then we have a relative calibration system on board, and that is partly to compensate for transmitter power variations and also partly to compensate for differences in between the different GNSS constellations. And so our goals were to demonstrate these and also the onboard DDM processing, and to do all this on a 3U CubeSat. And then the batch 2 goals were to evolve the batch 1 into a more operational system, increase the number of land observations by a factor of 2 through the use of a third antenna panel, and so increase the effective field of view. So we're processing about 30 observations simultaneously on these satellites, because we want to increase the value per satellite by processing the maximum number of reflections. and that's partly required to make the most of the multi-GNSS constellation. So this is one of the key characteristics is of our payload has been tracking of multiple GNSS systems. The more transmitters improve the coverage and so the value per receiver. However, different transmitter characteristics are there, like the different modulation and the different signal power. So to produce comparable observations, we use our relative calibration system, and we pulled out a couple of tracks here over the ocean, one of GPS and one of Galileo, and we can see the characteristic BOC11 side lobes. And we perform, as part of our calibration and validation, interconstellation pairing to validate the observations between constellations. And we can see for the normalized bistatic radar cross-section, the difference between GPS and Galileo of, on average, bias of 0.1 dB. And over the land, which is bistatic radar cross-section and not normalized by area, about 1.1 dB difference. So we think that the difference is related to the difference in scattering area, rather than something internal to the receiver. So here I show a map of the averaged reflectivity, so the L-band bistatic radar cross-section over land and the normalized bistatic radar cross-section over the ocean. And the data is gridded at 50 and 100 kilometers respectively over the course of a month. So we combine together the multiple GNSS constellations to achieve increased coverage per receiver, and then combine all of the 4 FMs to give a dense global coverage. One of the key goals of batch 2 was to increase the land coverage by a factor of 2 over batch 1. So on this, these images, we're showing the effective number of observations that occur simultaneously after quality control. So we're processing about 30 on board, but after quality control, we reduce the number, and that's partly because of low reflection areas, and partly where we include reflections at the edge of our antenna pattern. So the batch 2 is averaging 14 observations passing quality control in regions of higher reflectivity, and we expect this to improve as we refine our quality control thresholds, which are somewhat conservative at the moment. So with GNSSR, as already been discussed, it's got this great sensitivity to surface soil moisture. And here we show 2 of our regional views of our reflectivity gridded at 10 kilometers. And we're showing this 1 frame per month from the last, from 2021. So these are showing the expected seasonal changes corresponding to soil moisture and freeze-thaw state. And so we've, the density in the north starts coming online when the batch 2 satellites were launched partway through the year. So we've then taken these reflectivities and developed a level 2A soil moisture product. And so we generate soil moisture parameterization in an offline process from historical L-band forward scatter, reflectivity, and SMAP surface soil moisture. And this is masked by fixed water bodies mask. We perform then a CDF matching process, and then in an online process, we take our GNSS reflectivity observations and index into our parameter map to generate a soil moisture retrieval. So to give you a couple of views into this, the top graph here is showing 1 track across South America, And so we have the Spire GNSS reflectivity, and the red dots are the points that pass quality control. And then once we've performed our surface soil moisture calibration, we can see the how these correspond with a paired SMAP soil moisture and the correlation of these results. So then we can take this on using a different way of comparing these results, using a 4-month spatial temporal pairing. So this is now taking in a huge region of different surface covers and surface types. And we perform this pairing between Spire soil moisture and the mean of the SMAP soil moisture within 24 hours of our acquisition time. And it's showing a very good agreement over these regions of interest. We've also developed an ocean wind product, and this ocean wind product outputs ocean wind and mean square slope. And I'm not going to dwell on this one today, and instead go on to the grazing angle GNSSR. So this is taking reflections from our radio occultation satellites around the grazing angle, and so these are characterized by being the other side of the booster angle with right-hand circularly polarized reflections, and we process these with coherent 50 Hertz observations. So taking an advanced operational constellation and leveraging the existing RO system. So we have more than 25 satellites in various orbital planes taking these measurements, and so it produces a stable operational data collection and producing 2,500 or more events per day, ranging from several seconds to nearly 6-minute long observations. So we collect 50 Hertz IQ measurements, and we perform open loop tracking of both the direct and the reflected signals, dual frequency as well. And because this is coming from our operational RO constellation, we have a median latency of 90 minutes. And so we output a number of products from these. Level 1, where the data from the instrument is kind of raw from the satellite, and then we perform measurement georeferencing. And then level 2, where we extract height profiles, and another level 2 product where we extract ice extent and classification. So GNSSR for altimetry. The concept here is that your GNSS transmitter can be used to pick up the surface height. And we perform this by taking a modeled signal path, which is the computed distance based on the transmitter receiver position and specular point on the ellipsoid. And then we take the observations from our receiver as the actual signal path, and that then subtract these two, and we get the target measurement, which is the surface height. And this is working for these coherent reflections over over smooth surfaces, because we're using the carrier observations. But it gives a relative surface height measurement, but because the GNSS signals are fairly narrow band, it doesn't give an absolute height measurement. So we're collecting these observations predominantly targeted at areas we expect to have highly coherent signals, so that ice and also some regions where we expect to see calm ocean. And we're seeing median RMS height differences of 22 centimeters. So that means that 83% of our surface retrievals, surface height retrievals, agree within 50 centimeters with respect to the reference surface model. So the surface height retrieval, we are collecting over ocean, and the next step that we're trying to get to is towards getting sea ice freeboard. And we've got additional applications that we're targeting, which is measurements of the open ocean and also of the ice sheets, where we're using a digital elevation model, and we're seeing our measurements and the digital elevation model having excellent agreement. So the other area that we are targeting is the ice surface classification. So we've got all these different observations because we're collecting conventional GNSSR, and we're also collecting a coherent grazing angle GNSSR. We've got observations that are at dual polarization in between these two types of satellite, and also dual frequency observations for the grazing angle. And we've got diversity as well in coherent processing and incoherent processing, and a diversity of geometry, grazing and around nadir. And this provides a unique set of information for characterization of the ice surfaces. And so we're seeing high resolution data products coming out of our work for ice extent and ice type. And we can see these different observations. They've got really some very interesting different sensitivities to the types of the ice, particularly the excess phase noise, providing a lot of information about the marginal ice zone. And so we are taking those observations and comparing them as well to synthetic aperture radar images, and we're seeing a good sensitivity to the different types of ice between old ice, first year ice, and also ice-free regions as well. So I'm just finishing up now with the plans for the Spire GNSSR constellation, which is we are still improving our observations. We want to add simultaneous coherent and incoherent channels to extend the current approach of either one type of observation, coherent or incoherent. And beamforming is not currently operational on board the satellites. We want to make that operational to increase SNR for all our observations. And we're expanding the GNSSR constellation. So Spire plans to launch an additional 3 GNSSR satellites in 2022. And the other plan is to converge GNSSR and RO measurements onto the same satellite. I see the challenges are in how we commercialize Earth observation, though, in a way that at the moment there's a gap between funded research and development and through the sale of operational data. And the other problem that we have to face as a community is GNSSR observations have these very high spatial resolutions, 1 to 2 kilometers over land. But to exploit this resolution requires, with timeliness, requires tens of GNSSR satellites. So I think there's an opportunity, though, that we can exploit the synergies and the differences between the missions, like augmentation of the flagship single satellites like small SMAP and biomass with sensors like Cygnus HydroGNSS and Spire GNSSR, each contributing complementary observations. And then in the interest of time, I'm not going to dwell on these takeaways other than that we've got our data products and preview data products available through ESA Earth Online and some through NASA CSDAT. And we're striving to continuously improve our measurements, our observations, and to support the community by making our data available to people to extend these observations and the applications too.
Thank you. Thank you very much for this very nice presentation, very nice results. We have a question from Jonathan. He's asking the size of the Doppler delay map and of your satellite is as large as TDS-1 or similar?
We produce the delay Doppler maps on board at a smaller size than the TDS DDMs, and then we don't feel like we need quite such a large delay range because we run with a digital elevation model on board, so that provides a better reflection tracking. And then but then because of downlink budget reasons, we then only downlink a subset of the delay Doppler map that is processed on board, I guess in a similar way to Cygnus, producing a larger DDM area on board, and then downlinking a subset of that.
Thank you. It will be very interesting to see the results of the beamforming approach to improve the SNR. We will see in the future. Very interesting application. So I think that we can move to the next presentation. It's time to go. Please, Maria Paola. Thank you again.
Yes, thank you very much, Phil. Really nice presentation. Thanks again. The last speaker of this session is Hugo Carreno Luengo from the University of Michigan. He is going to talk about GNSSR experience from Cygnus, including freeze-thaw detection. And I believe Hugo has a recorded presentation.
Hello, this is Hugo Carreno. The title of this presentation is GNSSR experience from Cygnus, including freeze-thaw detection. Here you can see the outline. First, an introduction. Then I will briefly summarize the development and the validation of our recent freeze-thaw retrieval algorithm. And then I will describe the main results over different selected target areas within the Cygnus coverage. Finally, I will conclude with our main findings. Okay, the NASA Cygnus 8 microsatellite constellation was first proposed for wind speed retrieval over tropical cyclones. More recently, the Cygnus science team has expanded the scientific applications also over land surface. Thanks to the outstanding mission evaluation during the Earth Science Division in 2020, NASA extended the mission operations at least until 2023. If you have interest in the science team experience and the ongoing science team investigations, you can check our recent publication in remote sensing. Here, in this presentation, we demonstrate the potential of GNSS-Reflectometry for freeze-thaw surface state imaging in the new space era using Cygnus data. Thanks to the disruptive spatiotemporal sampling properties of GNSSR and the high inclination orbit of future missions such as HydroGNSS, GNSSR could support and enhance the study of organic carbon release and soil respiration, but also help to characterize long-term variability of carbon dioxide and methane emission at global scale. Okay, let's move to the next section. Note that changes in surface permittivity due to freeze-thaw surface state changes and how these phenomena impact the observed surface reflectivity form the cornerstone of the formulation presented in this section. We use Cygnus Level 1 version 3.0 data for the estimation of the surface reflectivity. Additionally, we use ACM WF ERA 5 LAN reanalysis soil moisture content and soil temperature data with Hawley frequency as the reference. We selected the first layer of the soil because both active and passive sensors at L-band have sensitivity to this layer. For the validation of the algorithm, we selected the SMAP Enhancer Level 3 radiometer 9 km freeze-thaw product. In the figure on the left, you can see the target area selected for this development and validation. Okay, the retrievals are based in our recent seasonal threshold algorithm. It evaluates the time series reflectivity relationship with seasonal reference frozen and thawed states, as you can see in this equation. We selected a grid of 0.1 by 0.1 degrees, and we perform averaging using a moving window of 0.1 at the steps of 0.1. Note that the frozen and thawed states are selected as the 10% and the 90% points of the CDF of the reflectivity at each pixel during both the whole winter and the whole summer. Okay. Two threshold levels are defined such that the surface state is frozen if the scale factor is above the freeze threshold and the surface state is thawed if the scale factor is below the thaw threshold. These thresholds can be varied parametrically to define the receiver operating characteristic freeze and thaw curves, using ERA 5 line temperature as the reference. Note that the sensitivity is improved for the highest confidence case, as we can see in the raw curve corresponding to July. The optimum point in the raw curve is selected at the point when the slope of the curve changes from above 1 to below 1. Note that this point marks the transition from more true than false detection to more false than true detections. Okay, in this slide we can see an intercomparison of thickness of observed freeze-thaw samples with a SMAP radiometer freeze-thaw product over the highest confidence areas of this target area in both February and August. This is the southern hemisphere, so February is summer and August is winter. The SMAP baseline seasonal threshold algorithm is applied using normalized polarization ratio radiometer measurements. Note that the SMAP reports the surface state as frozen if any SMAP sample within 1 month is frozen, so the SMAP maps correspond to peak detection maps. Overall, we can see that cygnus evolution generally agrees with both the SMAP product but also with the ERA 5 LAMP product. If you are interested in the details of this algorithm, you can check our recent publication in TIGARS, and here you have the link. Okay, now let's move to the next section, the results. So let's start with a short introduction. In this slide, we can see 2 maps corresponding to the global temperature in February and July. We use, as previously commented, ERA 5 LAN as our temperature reference. Also, we can see the target areas, the Tibet Plateau, the Andes Mountains, and the Rocky Mountains. The 3 target areas are within the thickness coverage. Note that there is a strong temperature gradient over the 3 selected target areas from February to July. In the future, thanks to the high inclination orbit of HydroGNSS, we will be able to study freeze-thaw surface state also in areas with much higher latitudes, covering Russia and Canada. Okay, in this slide we can see a surface elevation map at 250 meter resolution derived from the global multi-resolution terrain elevation map. Note that the 3 selected target areas correspond to high elevation terrain with elevations above 4,000 meters. We use this elevation map to derive the topographic roughness index. This is an interesting parameter also for the interpretation of our results, as I will show you in the next slide. So let's start with the Tibet Plateau. Here we can see the strong temperature gradient from February to July, and also the topographic roughness index. Over the Himalayas, the roughness is very high. However, over the central part of the Tibet Plateau, the surface it is really flat. Note that the Tibet Plateau is considered as the 3rd pole of the Earth. It has a great impact in water storage and supply in Asia. The dominant IGBP classes are grassland, barren and shrublands. But note that because of the climate change, the water bodies have been significantly growing during the last years. Okay, in this slide we can see results derived from our retrieval algorithm. These maps correspond to the number of frozen and thawed months in both 2019 and 2020. Over the Himalayas, we can identify permafrost, and within the Tibet Plateau, we can identify seasonal frozen ground. The 2019 and 2020 difference show that the 2020 surface temperatures were warmer over the Tibet Plateau, however, they were colder over the Himalayas. Okay, in this slide, we will analyze the time of the first freeze after summer and the time of the first thaw after winter. These are the freezing and thawing periods, which determine the flow of soil water, which has a strong impact in vegetation growth, but also in changes of land cover type. Overall, this has an influence on the frequency of the freeze-thaw cycle. The beginning of the freezing period appears sooner over higher altitudes. However, the beginning of the thawing period appears sooner over the central part of the Tibet Plateau. Okay, now we can move to our second target areas. This is the Andes Mountains. This is a quite heterogeneous target area in terms of both topography and climate, and it is covered mostly by seasonal frozen ground. The dominant IGBP classes are barren and shrublands. The topographic ruggedness, it is really high over the mountains, but it is low over the Argentinian pampas. Note that the climate change has an impact over the whole target area, but this impact is stronger over the arid Andes, reducing the water availability of millions of people. Here we can see the results. In this target area, the number of frozen months is lower as compared to the Tibet Plateau. It's around 3 to 4 months. Note that taking a look to these maps, we can see that the freeze-thaw retrievals depends on the latitude and the altitude, showing the capability of our algorithm also to detect regional changes. This result could complement few model-based permafrost study that has been performed in the target area. So this is also a future point to be studied, the complement of model-based studies. Okay, now let's move to the Rocky Mountains. This target area is covered with a wide range of climates from semi-arid shortgrass to alpine tundra. The dominant IGBP are grassland, evergreen broadleaf forest, and deciduous forest. The topographic ruggedness index is from moderate over the Rocky Mountains to low over the prairies. Here we can see the results following a similar strategy as in the two previous target areas. The number of frozen months is low, from 3 to 4 months, and the results are well correlated with the local topography. Note that during the freezing period, the first month when a frozen pixel is found in this target area is closer to the end of the year as compared with the Tibet Plateau and the Andes Mountains target areas. Okay, now in this slide, I also want to comment some global results. The temporal evolution of the station of the total frozen area at its region. We can see a repeatable variability with periodic changes from summer to winter. Over the Tibet Plateau, the frozen area is always positive. This is an indication of permafrost areas in agreement with previous slides. Note that the station of the thawing period is longer in the Rocky Mountains than over the Andes Mountains. And overall, there is an important trend, that is the station of the frozen area decreased from 2019 to 2021, except for the peak in 2021 in the Rocky Mountains. This is due to a quite cold winter in the area, and because this is an area with a lower extension as compared to the Tibet and the Andes Mountains, and then is more susceptible to yearly changes. Okay, and finally, I want to summarize our main conclusions. We have performed a study using 30 months of thickness data over 3 different high altitude areas. Results show the capability to capture both temporal and spatial variation of surface freeze-thaw parameters. The loss of maximum extension of frozen area from January 2019 to June 2021 over the Tibet is around 100,000 square kilometers, and over the Andes is around 40,000 square kilometers. Definitive conclusions about the impact of climate change will be premature. However, with these results, we demonstrate the potential of GNSSR to further understand the geodistribution and the long-term temporal variability of carbon dioxide and methane. This study has a great impact on both climate change action, but also on socioeconomic actions, including geopolitics. So thank you very much for your kind attention, and now it's time for questions.
Thank you, Hugo. Very nice presentation and very, very interesting and promising results. I'm giving a look to the chat. I do not see questions till now. So I was wondering, probably there is a strong effect of the topography over that region, right? So are you compensating, or do you think to compensate it in the future?
Over the central part of the Tibet plateau, the surface area is really flat, so the reflectivity is a good estimation. Over the Andes and some target areas over the Rocky Mountains, we have the effect of the topography, and in the future should be compensated. Yes.
Yes, I think that's a good idea. And but by the way, of course, permafrost and the freeze-thaw state is a variable addressed by HydroGNSS. So this is a very good input and a very interesting study in the same direction.
Yeah, I agree. This will be an interesting trigger for the potential synergy with HydroGNSS future missions.
Hi, Hugo. I also have a question. Forgive me if I might have missed this, but I mean, have you validated these retrievals with some sort of independent data from SMAP? Or?
Yes, we developed and validated the algorithm over small target areas over the Andes Mountains, and we compare our retrievals with SMAP and also with ERA5. In the future, we will include also the potential use of ground truth data over maybe the Tibet Plateau and the Rocky Mountains, and this is also future work. But at the moment, we have validated the product with SMAP and with ERA5. Yeah.
But this was only on one target area, not on all of this.
Yeah, this was validated over the Andes Mountains, and we applied the end results over the different target areas within the thickness coverage. Yes.
Okay.
Probably I can add that with HydroGNSS, we are considering in situ data. The FMI is considering in situ data network for this kind of validation. So this could be an added value.
Yeah, it will be very interesting to have some sites with real ground truth data. Yeah.
Yeah.
Maybe I can ask another question or rather comment from Hugo. I mean, Hugo, given the innovations of HydroGNSS, which are essentially, the dual polarization, but also, I mean, the L5, E5 signals, do you see any potential from these innovations with respect to freeze-thaw based on the experience that you have?
Yeah, actually, the use of dual polarization could trigger the use of two polarizations to remove or partially remove the impact of surface roughness in the retrievals. So this is an interesting point to be analyzed. Yeah. And also, if I understood correctly, you are planning to change the attitude of the satellite so as to exploit in a much efficient manner both the left-hand reflected and the right-hand reflected signal. So this is also a different, an additional characteristics from HydroGNSS that can be exploited for this product.
Okay, thank you. Thanks, Hugo.
So this is the end of this session. Thank you very much to the audience for attending. Please, Peter, the floor is yours.
Thank you, Davide, and thank you, Maria Paola. Excellent co-chairing for this session. Thank you to all the presenters for your preparation and delivery and the really interesting topics. Good to see all the additional work that's going on in other GNSSR missions. So we're bang on time, which is great. So I think we'll come back together at 3 o'clock UK time for the final session, which will conclude the further research topics, and we'll complete the workshop with the roundtable discussion.